Okay, so welcome back to lecture after a long break, right? We had quite a long break. The last lecture we had was a revision lecture, so no real materials. Then we had your recess week, then we had our midterm week. So this is like 4 weeks, right, of no new material. How's the midterm? I'm still halfway grading through lah. I only got through question 1 and 2. We'll see how it's like. Question 1 turned out to be not very good lah, in a sense. Maybe if you don't get the description correct, at least the big O notation, time complexity, should be able to get right. But it seems like most, I don't know, I've not analyzed the results yet, so we see how it goes. Anyway, this Saturday, your tutor will go through midterm and PE. Okay, so there's no tutorial file will only be released today. So Saturday is too short a period for you to be doing tutorial 5. Okay, so we will do midterm revision. Then following Saturday, then we will continue with tutorial 5. Okay, so tutorial 5 will cover today's topic, which is abstract data type. Okay, so just some roadmap, like, so this will be what we had in 101. So actually we saw this earlier as well, right? So we already covered composite data, struct and multi-dimensional array, nested loop. We also talked about recursion and learned about complexity. Okay, so with this we did sorting and searching. Okay, so but searching we did binary searching, which can be done using some kind of recursion as well. Okay, so all this is what we have covered, right, before the midterm. Okay, now we are going to abstract data type. Okay, then from there we'll go into collections or all the rest of the things. Okay, so today we're looking at abstract data type and maybe a little bit of the C standard template library. Okay, what is this standard template library? Okay, so the schedule, no change from before. This one, week 13, is the revision lecture. Lecture. This is supposed to be some wellness day or something. Okay. Anyway, revision lecture is an optional thing lah. So we will have just a revision lecture. You attend or don't attend, we're not teaching much. Okay, so we will just make use of the wellness day. Take note, practical exam 2 is just after Good Friday. Okay, so after this Thursday revision, Friday is Good Friday, and Saturday we come back, okay, for our second practical exam. Okay, final exam is somewhere in the exam weeks. Right, so far we have only been dealing with simple data in a sense, right? Okay, so numbers, arrays of vectors, and structures. So array of vectors, right? Okay, and structures. Of course, there's also strings lah. String, array, vector, string. Okay, so life is complicated in a sense. Okay, so we need to have real life data. Okay, actually, we did talk a little bit about more complex data. Right, when we talk about structures, this is where we allow using primitive data to put together some kind of structural record. Okay, so one example of abstract data is, for example, the NES registrar has some record of students. Okay, so you can imagine a student to have information like personal information, which modules to take, what grades, and all that. Okay, so this record could now, I mean, in the past it's some paper folder lah, so today will be some electronic document. So the record would be our compound data. Okay, basically a struct, okay, which actually binds data together. Okay, so now the question here is, if you have a compound data with struct, okay, you put together with it, how do you access the data that you need in the struct? You need to know what are the fields of the struct. You need to know that the struct has this string, dot, name, dot, grade, things like that. You need to know the structure of the struct. Okay, which means you need to know how it's defined. And whether you change one field of the struct, does it affect the other? So these are the things you need to know about the struct. So the idea behind abstract data type is, would it be great if we can just abstract away the details? We don't want to know, we don't need to be bothered how the struct is defined. Okay, we just can make use of it. Okay, so that's the idea of abstract data. And where have we seen this before? Okay, we have seen this before when we talked about function abstractions. Right? So function abstraction, okay, was invented to make tasks easier to solve the solution. But in an abstract function, you don't need to know how the function works, but you just need to know what it does, and then you can make use of the function. This is basically the internals of the function is abstracted from you. Okay, so the irrelevancies are hidden away, so usage is separated from implementation, and so on and so forth. Okay, and can use building blocks for more complex functions. Functions can call other functions. It turns out that data can be organized the same way, all right, as functions. Okay, so function abstraction and data abstraction, basically these are the same. Okay, and while functions serve as building blocks for more complex function, data can serve as building blocks for other compound data. And so they are basically have the same properties. So data abstraction just do the same thing with data. Okay, so now what is this notion of abstract data type? Okay. So an abstract data type basically is you have some data. Okay, the datum is plural of data. Actually, sorry, data is plural, datum is singular. Okay, datum. So you have some datum, right? So which usually is a struct to contain all the information that you need, and the record, and you couple it with some operations. So together with these two, okay, we have what you call an abstract data type. Okay, so in an abstract data type, you have specification and implementation, right? Just like functional abstraction. Specification means telling you what are the operations you can do with this particular data type. Okay, and then implementation is basically how it is actually coded out. All right. So for ADT, generally to work with ADT, you have this four lah. Actually, generally 3 important ones, but here we list down 5. So the first important one is a constructor. Basically creating the compound data. How to create. Okay, and then you need to have some way to access the individual components. Okay, to access the components of the data, and you have ability to mutate, change, okay, set the values, the different components in the data. All right. Now these two, as you can imagine, one, if you are able to access or access the data, these two actually comes from here, right? Because predicate is basically just asking some true false function. I mean, obviously, if you can access to the components, you can write your own predicates. Printer just to display. Okay. So let's do a case study, like, to further illustrate what I mean by all this what constructor and all this kind of thing. Okay. So let's see. So let's use the C++, okay, or C primitive type. For example, int, float, double, char, bool, all these are primitive type. Okay. Now internally, all of them are implemented as bytes. Okay, because as we all learned last semester, everything in the computer are just 1s and 0 bytes. Okay, so internally your float, okay, is represented this way. Let's see, I move it up a bit. Okay, like that. Okay, your float is represented, okay, in some representation. We did gloss over this last semester, right? We say, okay, so these are the bits. So a float is 32 bits. This represents the fraction, so on and so forth. This is the implementation. But just like functional abstraction, you actually don't need to know this implementation, right? You don't need to know how it's exactly represented in bytes in order to use float. You just use float, right? One this float plus that float, right? You just use it in a normal operation. Okay, so that is basically the details of the data is now hidden away from you, abstracted away from you. Okay, so let's take a look at second case study. So this case study, we call this points. Okay, now we create our own data called points. I think you have seen points before, right? In your what's it, midterm, right? I think midterm. Okay, we use a struct, right, to represent row and column as a point. Okay, so that one is not exactly abstract data type; it's just compound data. Okay, so now let's see how we can further enhance, okay, this points data that we have to make it an abstract data type. Okay, so points in an xy plane. So let's say we have points xy. All right. So let's have some wishful thinking. Assume we have a point ADT. Okay. So now is this data type is called point. Okay. Internally, whether it's a struct or not, or how it's represented, we don't need to know. Now we are given these few functions, okay, to manipulate this data type. So the function make point, okay, creates a new point, okay, or rather you Okay, this is so you put in you pass in an empty point, and the x and y, you will set the x and y of this. Okay, of course you can always have this return new point. That is also fine. Okay, and then with accessors, let me see if we can do it with make point. Okay, that's for later. Right, so now with a point, you want to access the x and y of a point, you do x off and y off. Okay, now here we use reference, just basically to avoid copying. Okay, so x off and y off will give you the x and y coordinates of the point. This is the accessors. Okay, how about to set the x and y? Maybe you can use mutator. Set x and xy. Set x and y of a point. Okay, so this one takes in the point, sets the y x value of it, sets the y value of it. Okay, so okay, why does point have to be referenced here? Right, basic. Okay, this one definitely have to be referenced, right? Right, because I'm mutating, I need to modify this point. Okay, so it has to be referenced. Here you put reference, but I put constant. Okay, so basically this tells you that I don't make a copy, but this is constant, meaning this function x of will not modify this point. Okay, so this is why we have this constant reference here. Basically, this reference just to save the copying time lah. Alright. Now, assuming we have these three things: constructor, accessor, mutator. Now let's create some new operation of a point. We want translation, we want rotation. Okay, so how to do a translation of a point? Right. So suppose a point xy, you have to translate by delta x and delta y. Okay. So to translate this point, you just basically you plus delta x plus delta y lah. Okay. So maybe you have this thing. Okay, let me just move this. Oops. Okay. So so we have this function called translate point. So we take in a point that we want to modify, delta x, delta y. Okay, so this will change our point. So how do we code this? Well, basically, just set the point of p, okay, to x of p to dx and x of y to this. All right. How about rotating around a point? Rotating is basically you want to rotate by theta. Okay, 45 degrees. You have this formula lah. Right, just some formula. So basically, include math and rotate a point. You have this formula. Okay, this is how you rotate around a point. Display point basically just display the x and y lah. Okay. Now with so let's demonstrate to you this point. So how do we make use of it? So suppose in main, right? So I have a point p. So I create a menu point. I initialize by doing make point. Okay. So I can display the point. Then I translate the point. I display, rotate the point, and display. So obviously you can run this and you get all the points. Okay. Now you might ask, what's the point of having all this x off, y off, set x and y? You know, so what's the point of having all that? Okay, right. So at this point of time, okay, we do not know how make point x off. Basically, how this is is defined. Okay. But we can define new functions, right? New operations. Okay, we don't know exactly how a point is represented, but we can now define new operations. So this is basically the power of abstraction. That's like functions. You don't need to know how the function or data type is implemented. We can still make use of them. Okay, so I've showed you now we can write new operations without actually knowing the implementation of a point. But what's the point, right? Why do we need all these accessors, constructor, mutator? So troublesome, right? Why don't we just do this, right? Why don't we just do point dx dy, just p dot x plus equal p dot y? Basically, this is what you did for midterm, right? Right, you find the up, down, left, right. You will just do the px p row plus equal 1 or p row minus equal 1. This is what you do, right? In the midterm. So the question is, why do we not want to do it this way? Why go through all the hassle to do the x off and then set x? Okay, so why shouldn't this still work? Okay, Now let's come to this realization. When I say a point on a graph or point on the plane, does it need to be in XY representation? XY representation is called Cartesian representation, right? Where you have x here and y here. Okay, but actually in maths, there are other ways to represent the same point. Okay, for example, we can use polar representation. Basically, what is represented, how to use polar representation. So you say this is the origin, right? 0, 0. There's the x-axis. There's the x-axis. You rotate by this amount of degrees, 71.6 degrees, and you go this 3.16, the length of this. You will still arrive at the same point. Okay, so this is called polar coordinates. Okay, so there is no reason why your point should follow the XY coordinate system, the Cartesian coordinate system. I mean your data. What if I decide to have a struck point, right? And I use polar coordinate system to represent this point. Okay, then in this case, to make a point, you put in double x double y lah. Then I have I put in xy Cartesian coordinate here 1, 3. I do my conversion, I hypotenuse and do the arctangent to get a distance and angle. So my point convert into polar coordinates. Okay. If this is how I actually make point or represent internally the point, okay, what happens to our translate function that does this? You have compound error, right? Because how do you even know p has a dot x dot y? It does not, right? My point is now angle and distance. So your translate function now cannot compile. It's outdated. Okay, so the contents of x and y now represents different things. Okay, it doesn't even have x and y. Okay, so what happens now is the error you commit here is called breaking the assumption. Okay, basically you are making some assumption about the organization of the data type. Okay, so that is not what we want to do. So we want to view data as a black box. We don't want to dictate how the data is implemented, right? So when we access it, we cannot make any assumptions. At least there's compile error or some problem. Okay, so the question now is, why even have all this different implementation? Okay, a point is a very simple example. Basically, it's the simplest thing I can find that has two well-defined definition, a well-defined how do I say that? A well-defined representation form. Okay, you can easily imagine, like back to our NUS registrar record, right? If I ask the registrar for a student record, okay, if I need to know the name, I will ask the registrar, give me the name of students, maybe the grades, module taken by student, all that. I don't need to know how the NUS registrar store the data. They could be stored in paper folders, stored in whatever document, database, whichever. It does not matter. If I need the information, I make sure I make the appropriate function call. Give me this particular student and all the modules taken. So they're returning maybe a vector or list, of all the modules taken. How it is stored internally, okay, it is not now my business, right? I don't have to care, right? Or not that I even want to care, right? As long as the registrar provides me the appropriate function to access the data, even modify data, right? I can set the grade, or for your course and all that. Right? So the registrar provides all this functionality. So that's how we want to approach data. Okay? So in our case for points, okay, suppose we have new accessor. Right, like I said, a point have x coordinate, y coordinate in terms of Cartesian plane, but we can also represent in terms of distance and angle. Okay, polar coordinate. So if you want to do distance and angle of point, then you can set distance and angle. Okay, so now we have many different ways to access a point and set it. Okay, we don't have to care how point is implemented. So if you want to do rotate point, now rotate point, very easy. Don't need to go and do trigonometry, right? Just say I got P, get the angle out and set the angle. Okay, and if we have a our translate point can remain the same. We get an X off, Y off, and do translation. So now it makes our operation, our custom operation easier, because we have access to now different ways of getting the data out. Okay, the translation, it all happens within point. So I don't really need to bother how point actually store the data. Whether it stores as struct, I also don't really know, right? Maybe it stores in some vector or some, I don't know, object or whichever. Okay, so the way that the point is now represented in the memory, okay, is now hidden from me. I don't need to know. All I need to know is what are the functions or operations available to me. Then I can write my own custom function using the most appropriate. So down here, rotate point, I don't need to deal with trigonometry, I just use angle. Okay. Internally, if point is represented as, I don't know, Cartesian coordinate or polar, then there will be some translation, going on in the background. Right. So that's the idea of abstract data type. Okay. And we have seen some abstract common data type in the C library, a C++ library, and we have been using this since last semester, right? So a vector is an abstract data type, right? How a vector is represented in the memory, we actually do not know. Okay, array we know lah. Array I've mentioned before is a contiguous storage in memory. So array, the one is exposed to us, but vector is not. Right, so I don't know how C++ organize a vector memory, nor do we need to know. Okay, okay, we need to know how a vector is defined. So this is called a template class. So later on in the future lecture, we will learn a little bit more of template. Basically, it's this type template, this thing like you can customize the type you want. So we know that vector, you put the type inside here. So this becomes an integer vector. Okay, so for vector, the advantages is dynamic sizing and automatic memory management. Okay, in a sense. So array is fixed size, right? We create an array is fixed size. We cannot change the size of the array midway. Okay, but for vector, we don't have to bother. So the implementation of the vector will handle this for us. Okay, so vectors. Okay, now we put all the common methods. Okay, here they call it methods lah, or function operations, or function of vector. So the constructor basically is just vector this thing, like vector the type v. Then you have a vector now, okay, available. Of course now it's empty. To access it, you can use add, or just this square bracket. Okay, add square bracket, front, back, and size. Alright. Access the first element, last element, get the size of it. Okay. They provide this predicate called empty that returns true if there's no elements. Or you can just use size lah. Size equals 0 is empty, right? Okay, so again, so this empty is just mainly for convenience. Front and back also mainly for convenience, because front is just at 0, right? Back is just at size -1. Okay, so this is just convenience functions for you. Okay, to clear also for convenience, because you can always pop back all the way until everything is gone, right? Okay, so there's a way to remove, way to add. Okay, into a vector. Of course, of course there's insert and remove lah, which add into arbitrary place. I didn't put down here. Okay, this is just some common methods. Okay. So now, why do we call this a template? Okay, so maybe we are covering here. So why do we call this a template container? Okay. So we know that a vector is container. We have been using it all this while. Okay. But what does it contain? Okay, so the values of the container need to be of a certain type. Alright, so in C++, I mentioned before, is a static type language, meaning any value or data that you create has to have a type. Okay. Other languages like Python, JavaScript, they are dynamically typed language. Means you have a variable. During the course of the execution, the variable can take on different types. It's like one moment it's an integer, next moment it's a string, another moment it becomes an array. So Python is dynamic type. Okay, so why the difference? In a way, C is a compiled language. Okay, so when a language compile, it will compile into machine code, right? So when the function is compiled, the compiler needs to reserve space in the memory to contain your type. And we talked about this, I think last semester we talked about it. Different types require different space, right? We know different, some need 1 byte, some need 4 bytes, so different type require different space. So that's why in C++, your variables you need to know the type and fix it so that the compiler can reserve space in memory, okay, when it's being compiled. Languages like Python and JavaScript are not compiled languages. Okay, we talked about it a little bit last semester. They are interpreted languages. So the space that they occupy in memory can be resized dynamically in runtime. Okay, they are not compiled into machine code that runs on the raw CPU. Okay, so Python and JavaScript, there's an interpretation layer. So in this interpretation layer, the memory, okay, it is managed, okay, by the software. Okay, as opposed to when you're compiled already, your memory become managed by hardware in that sense. Okay, so that's the reason why most compiled languages are strongly typed. Okay, they need you to just define what type this variable is. So at compile time, they can write the correct instructions, okay, to set aside memory. Okay, so this is the trade-off between compiled languages and interpreted languages. Of course, you can easily imagine compiled languages do run faster because they don't have a middleman doing the interpretation. Okay, so template here basically it's allow us to decide, right, what are the type the vector contain. Okay, so vector of int, vector of points. Okay, so this one we sort of understand, right? We can create a vector of points that is done in midterms and all that. Okay, so type is in the brackets. Okay, so a vector of points, vector points, point p. I can make a point p. I can put it. Okay, I translate the point p and I push it into my vector. Okay, so now I check the point sizes. I display the points and the end. Okay, what do you think I'll see? Maybe I'll just see all the p is 0 0 translate by 1, so it'll be 0 0. Then I will see 1 1. Then I will see 3 3, so on and so forth, right? Okay. Now the question is, I reuse point p, you see. I translate p, so just translate mutates p, right? It modifies p, right? Okay. So p, I push back p. Now the question is, how come the vector does not change? Why the points in this vector don't change? I'm pushing the same p into the vector. And I can answer. You know what's going on here? So here I have so basically here what I have is I have point p, right? So I p. Now Amanda asked, is point a standard template? Well, I don't know, right? Point at this point of time, I have not said anything about how point is defined. So point is an abstract data type to us, but point does not take in any special type. So no, point is not a template. Okay, not a template type. Template type basically means this type allows you to take in, okay, some other type. Okay, basically like vector allows you to specify what type you take in. Point has no template type. Okay, so that's what template type means. Standard template just means it's part of the C++ standard library. That's why they call it standard template. Standard library. So vector is a standard library. Okay, that's why you say using namespace std, std standard. Okay, so it's from this standard library. Okay, so point is a abstract data type. So vector of point. So I have point p. So p is a point. Okay, so p is some pointer. I mean, I don't know how it's abstracted. I have to draw a box. So at first it's 0 0, right? Then I push p into my vector of points. A vector of points. So maybe the first thing. When I push in, is it like this? I push p in. Maybe I just do my erase. My eraser, Control E. Okay. Okay. How do I get back my pen? Control P. Okay. So I put p inside, right, my point. Then I translate 1 1. So p becomes 1 1, right? and I put P inside. Then I translate again, 2, 2. So this will become 3, 3. Then I put P inside, right? Why won't all this P end up? So at the end, I think after plus 2, plus 3, plus 4, plus 5, you end up 15. I think, or less than 5. So 1 plus 2 plus 3 plus 4, right? You end up being 10, right? Why won't my point vector be all 10, 10, 10, 10, 10? Why when I print out, it will still be 0, 0, 1, 1, 3, 3, 6, 6, 10, 10? And that's what this question is asking. So P is reused. How come the points did not change? Already saved in the vector point. Yeah, what's so special about this vector point? The pushback pushes by is not only the for loop, right? So I put P here. I push P back. So P. End of day P is 10, right? How come when I go around and I print, right? Try to access this P. This is not 10, 10. This is 0, 0. Right? Okay, so Angel said yes, it's passed by copying. Hey, if you remember vector, when you put something in the vector, it is passed by copy. It's not passed by reference. Okay, so what is stored in here is a copy of P. So back then when P was 0, 0, a copy of 0, 0 was stored inside here. Okay, it is another point. No? A copy of 0, 0 is stored inside here. Okay, copy is stored inside here. When I pass in 1, 1, a copy of 1, 1 is stored inside here. So it's important to note this is passed by copying. Okay, that's why I can change my P. It does not affect what's inside here. Okay, so this is the reason. Okay. If you want it to change, there's no way to force this to pass by reference because that is defined by the function. What you do is you pass in a pointer. And that's why later on we will see ourselves making quite a bit of fair use of pointers. Because pointer allow us to pass in something in here, a pointer that points to the original item. Okay, it's not a reference. Because reference has to be defined by the function. Okay, so that is our vector. Let me see if we can take a short break here. Okay, let me go through stack ADT lah. Okay, we finish stack ADT. Okay, then we will take a break after that. Okay, so it's only about half an hour-ish has gone. Okay, so now that is vector ADT. Let us try to create a new data type that we call stack ADT. So today we will be learning about stack, and later on we learn about queue. So what's a stack? Okay, a stack is basically a specialized list, a specialized sequence. All right. Now, what's so special about this? Is like imagine a stack of books. When you add to a stack, you can only pile on top. Right? You cannot put things into the middle of the stack. Cannot. Well, it's a stack of books. You can pile on top. And when you remove, you can only remove from the top. Right, so it's quite constrained, right? So it's basically rather more constrained use kind of database. Now, why would you want to use a stack and not use a vector? Because basically, if I have a stack, then I'm guaranteed nobody can just take things out from the middle. All right, so I have certain kind of guarantees and protection over this data type. So a stack is sometimes known as last in, first out. Okay. So you can add and move on top. Okay, besides remove on top, you can only see the top book. So basically, this is a stack. I put a book here, right? I can only see what's the title of this book. Okay, I cannot see what's inside the rest of the book. Okay, of course, I may be able to keep a counter. Like every time I add, I can count how many books there are. 1, 2, 3, 4. Right? But I cannot see the value of what's inside the stack. So a stack is known as last in, first out order, because the last thing that was in is the first one out, or something they call it first in, last out, philo order. Why is first in is the last one to be out. Okay, so this is the stack. Now, what are the operations stack can support? Okay, so basically you Okay, so besides constructor lah, you need to find a way to initialize a stack. Okay, so an empty stack is created. You need to push the element onto the top stack. They call it push, because okay, you think of it as some kind. Don't those sometimes you have those buffet table. You have this plate dispenser, right? Then inside got some spring, right? Okay, so you have to put more plate on top. You push a plate on top. So then when you remove, you just pop it off. Okay, so basically push and pop. They both start with P lah, so maybe that's why it sounds nice. Okay, push, pop, and peek. Okay, so push, pop, peek. Let's peep at the top of the stack. Okay, so basically these are the three main elements. Okay, empty. Basically, okay, depends on peek. If peek return top element of stack, how do you know whether peek will be empty? So you peek into empty stack, probably you get some error, right? Because peek returns top element of stack. If there's nothing to peek, then what should peek return? Okay, so it may crash or may have some error. So the issue is you need this empty function, okay, to return true if stack is empty. Okay, so how to use the stack? So basically, let's create a stack, okay, of integers. So down here, our stack is definitely a template function, because stack contains things, right? Things to push inside, and with everything in C, it needs a type. So we use this template, okay, to help us define what are the types that this stack will contain. Okay, so I push 1 into S, so my stack have 1 inside. I push 2, so 2 is stacked on top, right? I push 3, 3 is stacked on top. Okay, now is S empty? No, not empty. It has 3 items inside. Okay, when I pick S, what will I see? I'll see 3, right? Okay, because 3 is on top. If I pop S, this get popped. So 3 will appear, pop out. Pop S again, I get 2. Pop S again, I get 1. Okay, now is it empty? Yes, it's empty. I have to say true. Okay, so this is basically how you use the stack. Okay. Now that we know roughly what are the operations a stack should support, let us try to define or create our homemade stack ADT. Okay. So one way we can use this stack ADT is basically just use a vector, right? Stack appear to be a vector, right? Some vector, right? Because vector is like list, stack is this. So we create a vector to use our stack, and where should the top of our stack be? So for a stack, normally there's a top of a stack, right? They call it top, where you push and peep. For vector, I think the easiest, as you realize, the vector is you push and pop from the back of the vector, because when you put add and remove from here, you don't need to do any shifting. So your operation occur in constant time. Now you understand about time complexity. If you do it at the tail, it's constant time. If you add something into the front, this is actually O linear time, right? Where n equals to the length of the vector. Because to put something here, everything must shift down 1. You must go down and do a copy. By doing this copy, the number of time there will be some loop lah. The n times, where n is the length of this vector. So to add and remove from here incurs O n time. Whereas to add and remove from the tail back, we incurs O 1 time. So we will just use this part here lah. Use O 1 time here. Okay. So how to define our stack? Right. So what you just need to do is our stack has to be a template data type. Okay, template data type. So we use this word here, template. Okay, type name T. So T is the placeholder, like some like a variable. So T is your type. Okay, so I will have a struct called stack. So why we have this template T here? Because whatever type our stack is, we want it to be the same type for the vector. Right? If I create a stack for integer, then internally I want to use a vector of integer. If I create a stack of bool, then internally I want a vector of bool. Okay. If I want to create a stack of points, then internally I need a vector of points. So this T here, this tells the compiler that whatever T is supplied during the execution, I will use the same t and my internal vector here. Okay, so basically this is a struct. So our stack is basically a struct. Okay, that contains only one property, which is a v. Okay. Now we have to write some functions to add this into the stack. So push stack s with some value. Okay. Again, template name t here, because only the same type can be put into stack, right? So down here I'm saying I take in the input of stack of type t, and this was the value of type t. So this t matches, right? Because this t matches, we can push back into, we will push value back in, because this v will be type t, this value will be type t. Okay, so during runtime, if t is integer, then value must be integer. Therefore, this integer value can push back into a vector of integers. Okay, so this push back to pop, okay, is similar. So pop here, we take this stack, we look at the back, can get the back of stack and the value, then we pop back. Okay, then we return the value. Alright, and notice the return type of this pop is t, whatever t is. Okay, peak basically just return the back. Okay, empty is the stack empty, return whether is it vector has this empty function, okay, which we can use. Alright, so now our stack, let's look at the performance. As I mentioned before, pushback, popback empty is O1. Okay, O1 because vector maintain a count of contents, right? Vector does not have to go through and count 1, 2, 3, 4, 5 how many there are. As you add delete, vector maintain a current count. Okay, so empty basically just checks whether the count is 0 or not. Okay, so stack very good. O1 for everything. Okay, so we'll come back after the break. We'll take a short 10-minute break, and when we come back, we'll look at Q, okay, or QAA. Q, okay, yes, stack only return the value on top. Okay, so there are specific cases where we want to use a stack, so we don't actually want the accidental access into the contents in the stack. That's why we are restricting ourselves. Okay, as you do your tutorials and your problem set, you realize there are certain situations or algorithms that we only need to use a stack, or we want to use a stack. Okay, because stack allows us only to access at the top, so it provides certain guarantees, okay, against accidental removal or modification in the middle of the stack. Okay, next round we'll look at Q. Q is very similar to stack, but it works a slightly different way. Okay, so after the break, we will come back and look at Q. Okay, so we continue. Maybe some process crash. Okay, anyway, this is a QAA. Now, what's a QAA Q? This is a very famous Q that we had, right? You all who should be old enough to remember this Q. What's everyone queuing for? Do you all remember or not? You just review your age. No, not before lockdown. You're queuing for the Hello Kitty toy. Okay, maybe Wan Ning too young already. Okay, Feng and Danny remember Hello Kitty toy. Yeah, now can order online. That's why now no more queue. So this is the first time this happened in Singapore. I mean, nobody expected got such a queue. You know, even McDonald's didn't expect. You know, so you notice that there's no police or crowd control, right? Nowadays, like if you have a queue like iPhone launch or something, right? You see there is some Cisco police or the auxiliary police, right? They will have crowd control. They'll set out a barricade and all that. So last time, no one expected the queue. Now COVID, the queue was 1 meter. That was, okay. So last time, no COVID, no crowd control. You see, they had queue in the car park. It was crazy lah. No one thought that people will queue for a cat with no mouth, mouthless cat. So now what's a queue? Again, the queue like stack is a specialized list, right? So a queue is a first in, first out structure. Basically, okay, in a queue, you have something called the front of the cube. Front, right? Or we call it head. You have what you call the back of the cube, right? Or tail. Okay, when you leave the queue or you get service, you leave from the front, right? So first person gets service and leave, right? When you join the queue, where do you join? Who joined the queue here, man? You join the queue here, sure get beaten up, right? Got fight, that's why. Queue cannot join here, right? Queue must join at the back, right? Okay, so a queue is a first in, first out. Some people say this is very fair. You are first here, you are first out. Okay, so this is the queue structure. What are the my Zoom really crashed. When was the last thing you saw it crash? It crashed with Zoom. Reboot, I don't know lah. It may take too long to reboot lah. Anyway, we have restarted Zoom already. Okay. Still okay, right? Spotlight. Okay. What are the question mark? Sorry, what does the phone say? Okay, so Q is first in, first out. Okay, so what are the operations a Q supports? Okay, so just as so in stack you call it a push and pop operation. Basically the insert and remove in stack is called push and pop. So an insert and remove of Q is called NQ DQ. Enable and deable like NQ DQ. Okay, essentially just insert and remove lah, but they call it NQ DQ. So NQ insert in the tail, DQ is removed from head. Okay, and to look at the front of the Q, they call it head. Either head or front. Okay, again, can be called front, can be called head. Okay? Empty return empty. So to use a queue, basically you create a queue. Okay, so queue has to be template data type because you put things inside. Okay. So you enqueue 1, enqueue 2, enqueue 3. So you have 1, 2, 3. Is it empty? No, it's not empty. Right? What's the head? Now it's 1. Okay, because the first one in is the first one out. It's 1. DQ, you get 1. DQ, you get 2. DQ, you get 3. And now it's empty. It's empty. Your queue, nobody else inside. Okay, so this is a simple operation of queue. Okay, let's use our homemade QADT again. So let's use a vector. This is similar to stack. Okay. Now to enqueue, we say to enqueue you join a queue at the back. Okay, so you push back. Okay. Now to remove from the front, what do you need to do? Okay, so you remove from the front. Okay, so to DQ, you take from the front, right? So this one. So suppose A1 is the item in the front. Okay, we remove from the front. Then now we need to move everything up. We need to manually move up. Okay, of course you can say, what about the remove function in vector? Vector I can always say dot remove. Right? Okay, imagine no have that dot remove. In any case, the dot remove does the same thing here. Okay, so imagine you don't have the dot remove. What you need to do is you need to copy. So what we do is for I equals to 0. Okay, so you copy the I plus 1 into the I. Right? So copy the I plus 1 into 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 the I. Okay, finally, then you delete this. Okay, delete the back. Okay, so we need to go down and do this copying. Okay. Basically, this is the same thing that the remove does, right? So those who are familiar with remove, you will do q.v.remove bracket q.begin, right? right. This is the begin plus 0. Okay, so this is what you do. So remove does this actually internally. They have to move everything down. Okay, so why I show you this thing, okay, is so that you can figure out, easily understand. This thing does take time. Okay, head is just return front. All right. So this process, as I mentioned earlier, takes time to go down to move and copy everything up. Okay, so NQ is O1 because you push to the back, but DQ now is ON. N the size of Q. So if your Q have 1,000 elements, you remove one first item, everyone must move down, right? It's like those kind of seats, queuing seats. You sit on the chair, when someone, maybe for those at the barber or what cut hair, you sit in the chair. Then the moment someone leave, everyone must shift to the new chair, right? To maintain the queue. This is what you must do. Okay, so this can't be good, right? Because stack is O1 Q is O1 ON. No matter which way you see, as long as you use a vector, you have to suffer this penalty lah. One of the operation will be faster than the other. Okay. Now can we do better? Okay. Yes, we can do better. Since stack is so good, right? Stack is O1 for both insert and remove. Okay, both for push and pop. So the idea, let's optimize our queue. Let's use two stacks, okay, for the queue. One for insertion, one for removal. So basically, you think of it as inbox and outbox, or in tray, out tray. And sometimes your office you have this in tray, out tray, right? Or yeah, okay. Or maybe some of you have this. When I go and see, bring my kids to go see dentist. After you see dentist, you must bring your file to the front and put there for payment. So it's still manual. There's computer thing, but you still bring the file there. So you have this stack, right? So you have this tray, then you stack your file on top, right? Okay. So this is the stack, right? Because when you put it on top, it's really a stack system. But how the receptionist don't know who come first? She'll take the pile and she'll flip, right? She'll flip the pile. So she will flip the pile into an out stack. Okay. Then she will start processing this way, right? So that's basically what we do, right? So items you push in the stack. So say you want first, second, third, fourth. Okay, you push in the stack, right? Like this. So the first person who arrive, he put his appointment card or his file, whatever, on top. Okay, then this one stack. Then when it's okay. Oh, I got animation here. Right. So 1, 2, 3. Okay. Then the receptionist will of course remove items from her out stack. Okay, when she needs to process a call number or whatever she's doing. Now it's empty. What she does is she'll take this whole thing, right? She'll take out from the stack, and because it's physical thing, she'll flip, right? She'll flip it. So which is equivalent to us popping one by one, right? And pushing one by one. So just take and flip. Okay? Then now here she can continue to service, right? In the correct order already. And at the same time, while she's servicing, more and more things can put inside. Okay? As people come, they can put things inside. Okay, so realize that now my insertion is O1. My removal is O1. Occasionally, I will have this ON-ish operation to do this refreshing. Okay? Occasionally. Okay? So, over a long time, or on average, right, this will become a O1. Okay. So, you can put in and take out. So, O average, this becomes a O1 operation. And they call it amortized, right? Amortized, or on average lah. Okay, so this is how we can make use of two stacks, okay, to sort of improve the performance of a queue, okay, by using vectors. Okay, so let's look at this implementation. So here I have a queue. So internally it's no longer just one vector, right? As before, internally my queue I use two stacks in and out. So when I want to push thing in, I basically push it to in. Okay, I push it in. Now to DQ, basically if the out is empty, then I must do the transfer process. Okay, so begin the transfer. While the in is not empty, then I push into out. Okay, I pop from in, push into out. Okay, pop in, push into out. So this will loop until in is empty. Okay, once it's done, then I just pop from the out. Okay, so this is the DQ. Okay, of course, to be empty, both in and out must be empty. That means I have nothing. Okay, so this is the implementation of this optimized queue. Okay, so moral of the story. So that's why we learn about we need this ADT. Okay, this one is only ON some of the time. Or okay, in actual fact, if you were to go and calculate a compute, right, it is really on average O1. Okay, it's really on average O1. You can imagine, I mean, okay, our tutorial, okay, have some cases where you can try what are the different time complexity with all the different combination. Maybe I put n elements in, then I pop n elements out. Okay, you realize that also becomes O1 on average for each element. Okay, so in this case for Q, each element experiences O1. Okay, performance. On average, each element experiences O1 performance. As opposed to the previous one, every time you remove, you incur ON. Okay, here maybe once in a while you get this ON transfer, but after that it is O1 already. Okay, so basically the moral of the story is the implementation methods, right? So previously we have seen when we talked about time complexity, we talked about algorithm, right? We saw that the algorithm that you use to calculate your, to do your code, and to calculate the values matters, right? There are some algorithms that are more efficient than others. Okay. Now for data, you realize the way you store your data also matters. If you use some clever data to store and manipulate, yes, you can create a more efficient, okay, function. Okay, you get a more efficient performance from the data. So that's why we have abstract data type, so that the implementation of the data, okay, we don't have to worry. We can assume that whoever give us data type, they do their best and give us the most efficient way of storing the data. Okay, so as users, all we need to know is, oh, I just use a queue lah, I push and queue, DQ, and queue. Okay, so this is why, okay, maybe for stack, you might see stack, I just use a vector lah, because end of the day, I just push back, pop back on my own. Sure, that is fine. Okay, but queue, you want to go and implement your own queue, or you make use of some already available queue. So for queue, it's a little bit more complex. You can't just use a vector. Okay, because using a vector, you incur the penalty, okay, of a performance penalty when you are dequeuing. Okay, so here we use two stack and we wrap up. Okay, so our implementation is now hidden, okay, from those who use it. Alright, so that's the idea behind abstract data type. Why sometimes we want to hide away the implementation, because oftentimes there are efficient ways of doing it, but efficient ways has a little bit more complexity. Okay, and we want to hide away the complexity from the user. Just as how with functions, we sometimes want to hide away complexity. Okay. Okay, so the next part, I will just introduce to you some common ADTs, okay, that we have available for us in C++. Right. The implementation of it, okay, we don't have to look into it, but it can become quite complex. The implementation, you will look into it in your data structures module, which I think you will take after this. I think 2100, data structures and algorithm. Okay. So this one actually peels open the data structure and examine how it works. Okay, I've given you some idea by examining how an efficient queue looks like. Okay. You'll be going into more detail in your 2100 class on how the different things will be implemented. For example, map and set. Okay, so array, vector, stack queues are basically sequence type, right? Your elements have some ordering to it. In a sense, the ordering is the sequence. Okay, but there are some data collections that are non-sequence type, like set and map. So what's a map? Okay, a map, some programming language call it dictionary, right? Python, JavaScript, they call it a dictionary. So a map is not a diagram lah. It's not Google Map, the diagram kind of thing. Okay, a map is basically the mathematical definition of a map. Okay, so let me just make this make this a bit bigger. Okay, like that. Okay, so Okay, so a map, basically what it is, it is something that maps a key to a value. Basically, it's a bunch of key value pairing. Right, like I mean, SQL is some data, some storage, yeah. So basically, you have some key and some value. So it's basically a collection of pairs. Okay, that's what a map or dictionary is. Kind of like a table. So you can view this like a table, right? Keys and value. Okay, so this key will map to this value. This key will map to this value. Okay, and because of the way it is designed or constructed, accessing each key is on average O1. Okay, amortized O1 access. Wow. Okay, so there's clever things being done in the background. This one you will learn in 2100. What is the clever technique? For now, we just treat it as a black box. Okay, so keys have to be unique. Okay, so in these keys there are no duplicates, because if you have duplicate, let's say this is 2 and this is 2 and this maps to 3, this maps to 4, then I ask you 2, you give me 3 or 4, cannot, right? Okay, so there are no duplicates, okay, in a map. Okay, so it's not allowed. Okay, so the map, think of it as a table. Of course, values can have duplicate lah. Okay, only the keys must be unique. Alright, so to use a map, C++ provide this thing called a map, right? In the standard template library, you have this thing called map, because that's why you using namespace std, standard template library. Okay, so a map is a template with 2 types, right? Because there's key and there's value. So key and value can be different types. Alright, so basically this just tells me that my keys are integers, my values are strings. Okay, so you can do that. What happens is that basically it stores some key value pair in some sorted way. So the key minimally have to have some kind of ordering. So, okay, so internally actually they use some binary tree to store the thing lah, for fast insertion and removal and whatever, right? Okay, so there's internally, that's what it's done. How it works, okay, we don't go into that, as I said. Okay, so the advantages is very fast. Okay, O1, okay, so we treat it as O1 insertion, O1 removal. Again, dynamic sizing and automatic memory management, okay, in this map. Now, how to use it? Right, basically, okay, size, empty, clear. Okay, this is the same lah as vectors. Okay. Now to access the map, you inside the bracket you no longer put a index, because in a sequence collection data in a sequence collection, the index tell you where, which location, right? 0, 1, 2, 3, 4. But in a map there's no notion of ordering. Okay, there's no notion of ordering. It's basically the key that you want. So it's a table, right? So you put the key, you get the value. Basically, it's a table lookup, like dictionary. Look for the word, you get a meaning. Okay, so you look for the key, you get the value. So the value of T associated with key. Okay, so the value of T, type T. Okay. To add in, you just do this. It's like assigning, okay, into an index, but of course it's assigned to a key. Now this either up, if the key does not exist, then you insert it in. So you create a new key. If it exists, you update. The key has to be unique. So by doing this, you are updating the O value. Alright. If you don't want the key anymore, you erase. So this is different now. There's no erase in vector. It's only remove, right, from the vector. So erase. Actually, is that erase? Actually, I think there's erase in vector. So what happens is they do a linear search down the vector, find the item and remove it. I think that's erase. Okay, I may be wrong lah, but I think that's erase. So here you can erase. Here there's no notion of remove because there's no concept of position. Okay, so you only erase the key. And to know whether the key is in there or not, okay, what you need to do is use this thing called count. Count number of elements of key. Obviously, this will either return 0 or 1 because key is unique. You cannot have 2 keys, so either 0 or 1. And why they want to use this count is basically for compatibility reasons. Okay, so in this case, count is either 0 or 1. So to know whether a key is inside the map, you just count. Okay, if it returns 0, it's not in there. If it returns 1, then it's in there. Okay, so to use a map, basically, let's see, you include map, use the std, map of students, string to integer. Okay, so Ben 90 marks, maybe mark integers marks, Catty 67 marks. Okay, this will add Ben and Catty into the map. Okay, we can modify. Okay, so Ben from 90 marks now, he get 98 marks. Okay, and the number of elements is 2. Okay, so you access Ben, you get 98. You can erase Ben. Okay, then Ben is not there anymore. So the number of elements is just becomes 1. Okay, then you do students, the count Ben inside is 0. Count Catty is 1. Right? So this is basically finding if key exists. Okay. Okay. Now, next thing. So you have a map. So this part, okay. So you have a map. How do you access all the elements that you say stored in the map? Okay, for a sequence type, you can do for I equals 0. Right? Use the index. Okay, to access. Can't use 0 access. Use index. But map no longer have any index. What do you do? How do you get a list of all the keys to iterate? Okay, so in certain languages like Python, JavaScript, there is a function to get a list of keys. C++ is not so simple. Okay, basically you cannot iterate using index. Okay, you need to use what they call an iterator. Okay, a fancy complex mechanism called iterator. Okay. So iterator is advanced thing lah. So we will not learn how to use iterator. If you want, you can go and learn about it, but we will not use iterator. Instead, we will learn a fancy new for loop syntax. Okay, to iterate through a map. So now we learn fancy stuff. Okay, so before we can learn what is the fancy stuff, we must figure out, okay, what exactly is stored in a map. Okay, if we create a map, okay, what is stored? So actually, in a map, like we said before, a pair is being stored because it's a key value mapping, right? Key map to value. So basically, you can think of it as each row is one key value pair. Okay, one key value pair. Key value pair. Okay, so the structure of pair. So pair is a standard structure. Basically, have two types: first and second. Okay, first element, second element. So T1, T2, there are different types. Okay, so knowing that, to iterate through, we use a fancy for loop construct that is found in C11 onwards. Anyway, we are C11, C14. Okay, it has this. So what you do now? You see, for, so your for loop structure looks like this. For, then you have your map here. Okay, so colon. Here, what is this map? This student is a string, comma integer, right? So naturally, each element inside here will be a pair. So that's why this element is called a pair string integer. Okay, of this. So what happens is, as this loop, okay, this element will take on the different pairs inside this map. Okay, it will continue looping until no more elements in a sense. Okay, so name is element dot first, marks element dot second. I can print it out. Okay, so this fancy for loop structure. Those who are familiar with Python, okay, this is similar to the Python style for loop. Right, for variable in sequence. Okay. So you can write your own function, okay, to take all the keys of a map and put into a vector. Basically, I create a vector of string, then I iterate through all the elements, then I push the elements into my keys, right? Then now I have a vector of keys, and then you can use vector however you want to do. Okay, so that's map. Now this fancy for loop actually works for vectors as well. Okay, so those who come from Python, you will also, yay, now I don't need to iterate through for loop using index. I can use fancy for loop construct, okay, to iterate through for loop using the Python style way, right? For the variable double colon, of course, type, right? Double colon vector, and then this for loop will loop through, and the variable will take, okay, all the one by one from first one, second one, third one, okay, the value of in found in the vector, okay. Okay, so that is map. The next non-sequence type is called set, which is basically a mathematical set. So in a mathematical set, you just put items inside a set, and in a set, no duplicates are allowed. Okay? And in a set, there's no notion of ordering, therefore no index. So you'll be like, why don't you just use a vector? Yes, you can use a vector, but vector can have duplicates, right? So if you want to use a vector to model a set, then you must handle what to do when there's duplicates. Okay, and for vector to find duplicate or find existing item in vector is a linear search. Okay, so what set does is it gives us a fast insertion and removal. Okay, I think almost O1. Okay, fast insertion and removal for set. Okay, so use set, basically you just include set and you call set this side. Okay, so again, dynamic setting and automatic memory management. Okay, the key is now fast insertion and removal. If you try to use vector as a set, the problem is to avoid duplicates, you will go and search through the vector. That means your insertion become ON, right? You need to do a search through, where n is the size of the vector. Okay, so for set, you don't have to. There's some mechanism in the background to optimize it. Okay, so whatever you have for map, very similar. The functions are very similar in set. Just that there's no index. There's no way to access the element in a set. Hey, it makes sense, right? There's no way to talk about. There's no accessor element. You realize there's no add or the square bracket element for operation for set, because it makes no sense to access things for set, right? You can only count elements in a set, again, either 0 or 1. Alright, so to use set similar to map, I will create a new set and call it int, set of integers, a metric number without the alphabet. Okay, so insert 1, insert 2, insert 3. What happens if I insert 2 again? What happens if I insert 2 again? Okay, it will not be an error. Basically, nothing happens because it's already in there. Okay, nothing happens. So 2 is already in there, right? And this is the same in math, right? If your set S already contains 2 and insert 2 inside there, nothing happens. Will you overwrite? You overwrite the same thing, right? So what's the point of overwriting? Right not? Ignore overwrite. They're both the same thing because it's the same element. Right, so it's as good as ignoring. You overwrite is the same thing, and you overwrite the 2 with a 2, there's still 2. Okay, so this is the same as a mathematical set, right? You take a set S, you union with a new element, right? If E is already in the set, then you union with E, then S will still contain there's no change in S. Okay, this is the way in math sets work. Alright, so to use STL set, okay, so after adding 1, 2, 3, this one there's no error. Now the size is 3, right? Duplicates are not added in a sense, or it adds an override. Okay, again, no difference. The resulting outcome is no different. Okay. Erase elements, erase 1, erase 2. Now 3 is in there, 2 is not in there anymore. Okay. How to obtain all the elements in the set? Again, use fancy loop construct. Okay, since matrix is made out of integers, so this element must be integer. Okay, so this will loop through every element in the set. Again, you want to convert set to vector, then you just do this. But again, the set has no notion of ordering. So whatever comes out, okay, it can be any arbitrary order. Most of the time it's sorted, but it can be any arbitrary order. Okay, yes, the set will do a search. Okay, but the search is very efficient kind of search. It's an O1 level search. Okay, basically they use a technique called hashing, which you will learn in 2100. Okay, they'll do a search, but this search is using some hash function. So on average, after you amortize, it becomes O1 or very fast. Okay? That's the advantage you have over use your own vector and you do your linear search. The linear search is very slow, right? Go ON, where n is the length size of the vector. Okay, but set there is a customized code in the background, and again it's organized in binary tree. We'll learn a binary tree, I think, next week or the week after. Okay, so the structure, like we said, the way you structure data also plays a role, okay, in making things more efficient. Okay, so that's what happens in the background. All right. So in summary, okay, that's quite fast. Okay, we are ending a little bit early today. So in summary, okay, abstract data type is basically this data abstraction that we use, okay, to hide implementation. All right, it's like function abstraction, but we now use functions to access data, and the reason why is now we want to decouple implementation from usage. Why decouple from usage? Because as you can see, it can be more efficient ways of it provides more efficient functionality. Okay, rather than like using a vector where you do linear search. Okay, we can hide complex operations behind the accessor function. We can define different structure, okay, to contain the data. Just like we see in Q, instead of just using one vector to hold the data, I use two stacks. Okay, so behind the abstract data, the implementation can be made efficient. Okay, the implementation can make your functionality or operations more efficient. That's why it's now hidden behind black box. Okay, so people who want to use Q, they don't need to know how it's implemented. They can assume, okay, your implementation is efficient, then we just use it. Okay, so that is the nice thing about ADT. You can easily imagine a queue have this restriction where you can only remove from front and add to the back. Okay, but again, now it allows you to remove from front, right? As opposed to a vector. A vector you can move anywhere, but every time you remove, you incur pump penalty. All right, so C++ provide map and set again. Map and set, okay, can contain, okay, map contain key value pairings. Set contains don't allow duplicates, but it allows O1 access time. Basically, to check whether something is in the set is very fast, as opposed to trying to linear search down a vector. Okay, so all these are already standard data containers that is implemented in C. So you can just use them. Okay, they are in the C as standard template library. So you don't need to go and reinvent the wheel for this. Stack and queue are also in the standard template library. Okay, just that I showed you some possible implementation to highlight to you, right, why we have abstract data type. All right, so all these are available in the C standard library. Of course, there are more. I can't even draw a proper circle. Of course, there are more other types of libraries and containers, but these are the most basic ones that are commonly used. And of course, using all this, you can build upon more complex structure. Okay, maybe not for this module, probably for your software engineering module. Okay, you may be required to have more complex data type, just so that things will become more efficient. Okay, so you will use maps, sets, to construct, okay, more complex compound data type. Of course, you hide it behind abstraction layer. Okay, so the users, okay, do not have to know what the implementation is. Okay. Okay, so that's today's topic. Next week, let me see what's next week. What are we talking about next week? Next week we talk about collections.